Welcome, ladies and gentlemen, to this video lecture. So before we move on, let's take a look at another example. So this is a little bit of a negative example. So let f be a function from R to R, defined as follows. So f takes on the value 2 when x is less than or equal to 1, and the value 1 when x is greater than 0. So if you want to think about what this function looks like, if we just go think about what its graph looks like, it looks like this. So it takes on the value 2 up to and including 1, and then it takes on the value 1 further on. So if that is 1, it kind of looks like that. So here we see there is a discontinuity here at 1. Now the question asks, show that f is not continuous at 1 by showing that f satisfies the negation of the definition of continuity. Okay. So the reason why we are discussing this example is because there is something very important called a hidden quantifier that comes up. And if you are not aware of it, it might cause you some headaches in the future. It certainly caused me headaches in the future when I was learning this stuff. Okay, so let us start writing out the statement that we have to prove. So of course here we can see, if we look at the graph of f, this is a very simple function. There is a discontinuity at 1. So this function is certainly not continuous. So now we want to prove rigorously that this function is not continuous at 1. So we need to show that it satisfies the negation of the definition of continuity. So let's just write the definition of continuity out. So definition of continuity. So in this case, this means, or let's say continuity at 1. Definition of continuity at 1 says the limit as x tends to 1 of f of x is equal to the function value at 1, which in this case is, function value at 1 is 2. So if x were continuous, then the limit as x tends to 1 would tend to 2, but f is not continuous. So let's write out exactly what this means. So meaning that, so I'm just going to write out the definition or the meaning of the statement that we have written out. So again, we know what the definition of the limit is. That is, for every epsilon greater than 0, there exists a delta greater than 0, so that if f if x is within a delta distance of 1, then f of x is within an epsilon distance of 2. So here we have written out the definition of this statement. And before we can negate this statement, remember this statement says, or f would satisfy this statement, if it were continuous at 1. But it is not continuous at 1, and we want to prove that. So we must show that it satisfies the negation of this statement. So two things here are important. Firstly, notice here we have an implication that we will have to negate. Remember, the negation of an implication is not another implication. It is an AND statement. And there is something else quite subtle going on here. This x, this variable x, is not quantified. We're not saying for every x or or there exists an x, but it should actually be, and this is a quirk of the human language of English, that this symbol x is not quantified. And this phenomenon actually has a name. It is called it is what is called a hidden quantifier. So this x that we have here is actually quantified, but it is not explicitly stated exactly what the quantifier is. So this is what is called a hidden quantifier. So if you go to Google and you Google for hidden quantifier, one of the first things that come up is how important it is to realize that this is actually a hidden quantifier. And this is exactly the situation that we're in. And we see here March 2016, someone who are the authors, these authors, or this author Barbara Shipman, very recently 2016 published a paper in the Journal of Teaching Mathematics and its Applications exactly on how important it is to realize a hidden quantifier. So if we just read the first couple of sentences, mathematical conjectures and theorems most often of the form P of x equals implies Q of x. So here we've got some predicates depending on x, meaning for every x, P of x implies Q of x. The hidden quantifier for all x is crucial in understanding the implication as a statement with a truth value, etc., etc. So if you're interested, then you can go look up this paper, Subtleties of Hidden Quantifiers in Implication, by Barbara Shipman, and what she says there. So in fact, what we have here is a hidden quantifier, and I'm going to write this hidden quantifier in brackets. Actually, it should go here, so that it goes like so, so that for every x in the real numbers, if x is within a delta distance of 1, then f of x is within an epsilon distance of 2. So let me I made the cardinal sin again of not changing my windows, so let me write that down again. So here in brackets I'm going to write down for every x in the real numbers. So here is what is called a hidden quantifier. Hidden quantifier. And you see here, if you compare with Barbara Shipman's paper, here we have some predicate depending on x implies some other predicate depending on y. And this is exactly the situation that we are in. Here we have some predicate depending on x implying some other predicate also depending on x. So in this case here, this px would be this part and the qx would be that part. Okay, so now once we have realized that there is this hidden quantifier, now we can negate this statement. So let's say let's write down the negation. So before we do that, how do we write down the negation of a quantified statement? We flip all the quantifiers and we negate the predicates. And careful here we are dealing with an implication. So that requires special care when we negate it. So the negation is for every epsilon, so that becomes there exists an epsilon greater than 0. So that for every delta greater than 0. So here we've got there exists a delta, so we just flip it to the other quantifier there for every delta. So that here we've got this quantifier for this hidden quantifier for every x. So that becomes there exists an x in the real numbers, and now we need to negate this implication. Careful when you negate an implication. I'm going to write it down here small. What is the negation if I'm going to use this symbol for negation? A implies B. The negation of this implication is not another implication, it is an AND statement. So that is A and not B. Actually, let's not use that symbol. Let's write out the word not. And let's write it like this, not B. So here we have this implication that we want to negate. So the negation there is 0 is less than x minus 1 is less than delta. So the A stays the same, and not the conclusion of our implication, which is f of x minus 2 is greater than or equal to epsilon. Okay, so here is the negation of the statement that we have to prove. Okay, and now we're ready to write out our proof outline. So let's write out our proof outline. Proof outline. And remember, this is purely mechanical. You don't require any thought, or no thought goes into writing your proof outline. That saves you the time and effort to focus on what is really important and what is really difficult, and that is the parts where thought is actually required. Okay, so what do we need to prove? We need to prove that there exists an epsilon. So define epsilon as, and it should be positive. And what are we allowed to use in defining epsilon? We're allowed to use any of our previously defined symbols, but we don't have any previously defined symbols. So we're not allowed to use anything in defining epsilon. Then we want to show for every delta. So we say fix any delta greater than 0. Then we have to show that there exists an x. So we need to define it. So we define x as, and what are we allowed to use? We are allowed to use any of our previously defined symbols, which is this delta and this epsilon. So we are allowed to use delta and epsilon to define our x. And now we need to verify. So we need to verify that two things hold. Verify that, let's say 1 x minus 1 is in absolute value is less than delta, and number 2, that f of x minus 2 is greater than or equal to epsilon. So here we need to do some work. So over here we need to do some work, and over here we need to do some work. Whoops, that was not my intention. Okay, so this is half of the battle. So I'm going to pause the video over here, and in the next one we will complete this proof outline with a full proof that f is not continuous at 1. I will see you in the next one.